Hello everyone, I am Dr. M.K. Deore. Now this is the second lecture from the second chapter. Students, in the previous lecture, I discussed with you about the metastable state, the population inversion and the condition for the large stimulated emission. And today, I am going to discuss with you about the active medium and what is the condition for the light amplification. Students, in the previous lecture, I told you about the different components of the laser, and one of the important component of the laser is the active medium. The active medium is in between these two reflectors, or we can say that in between the laser cavity. The active medium having the very important role in the lasing action. The medium in which a light gets amplified is called the active medium. The active medium, it may be in the different forms, such as the solid, liquid or the gases. And according to the active medium, now there is also the classification of the different types of the laser also. In that active medium, it consists of the huge number of the atoms. But out of the different atoms in the medium, only a small fraction of the atoms is responsible for the stimulated emission and resulting in the light amplifications. So that the active medium is very important and there is the light amplifications. And due to the light amplification, there is the formation of the laser radiations which are directed in only one direction and which is known as the laser. Now then we are going to see about the condition of the light amplification. Now this is the diagram of the different parts of block diagram of the laser medium. It consists of the different parts of the laser system, and I have already discussed about the second figure of the energy level, in which I have discussed with you about the absorption, the spontaneous emission and the stimulated emission. Now let us consider a beam of the light when propagating through the active medium. That means in this active medium, when a beam of the light is propagating and when the atoms are incident on the unexcited atoms which are in the ground state energy, now then this incident radiation loses its energy. This loss of energy may be absorbed by the atoms of the material which are in the ground state and jump to the excited state. Now this process is known as the induced absorption. Those we have already seen in first chapter. An incident photon may causes the stimulated emission in one of these atoms here. Now that means when the incident radiations interact with the atoms which are in the excited state, that means you can say that the atoms which are in the metastable state, then there is a stimulated emission of the atoms, and during the stimulated emission it produces the 2 or more coherent photons of the same frequency, and these photon produces the 4 more coherent photons. That means in a previous lecture we have seen about The amplification of the stimulated emission, in which when the one incident photon interact with the atoms which are in the metastable state, then it produces the two coherent photons. When these two coherent photons interacts with the another two atoms which are in the metastable state, now then it produces again the four coherent photons, and in this way there is the multiplication, or you can say that there is the amplification of the photons, and these photons are radiations which are along the same directions, which having the same frequency with the incident photons. That means we can see in this figure. So all these photons are moving in the same directions and added to the light beam and increases in its intensity. That means due to this amplification, the number of the photons will be get emitted which are moving along the same direction, which having the same frequency of the incident photons, and due to that the intensity of the beam will be the increases, and due to that this process is called the light amplification. So now in this way, during the stimulated emission process there is the light amplification. Now let us consider if there may be the n photons per unit volume in the light beam. Now as the beam travels through the medium, some photons are absorbed due to the absorption transition and some photons are generated due to the emission transitions. Now here we will not take into the account the photons generated by the spontaneous emission, as these photons go in the random directions and do not contribute to the light beam propagating through the medium. Now we have seen that in case of that the spontaneous emission, the photons are emitted in a different directions, and due to that you can say that the different directions in the random directions, and these photons will not contribute to the light beam propagating through the medium area. That means these photons will not be useful for generating the laser beam. Thus we consider only the photons generated by the stimulated emissions here. Let minus dN by dt be the net rate of the loss of the photons from the beam as it travels through an element volume of the medium having the thickness as the x and the area of the unity. The net rate of the loss of the photons from the light beam must be equal to the difference between the net rate of the absorption and the stimulated emission of the transition. Thus we can write here the net rate of the loss of the photons, that is minus dN by dt. It is equal to be the difference between the net rate of the absorption and the stimulated transitions. That is the B12 into the rho nu into N1 minus B21 into the rho nu into N2. Now here the B12 is the Einstein coefficient of the induced absorption, B21 is the Einstein coefficient of the spontaneous emission, the rho nu is the density of the incident radiation, and N1 and N2 are the population of the atoms at the ground state energy and the excited state energy levels, that is E1 and E2. Students, we have already obtained the relations as the V12 it is equal to the V21. In first chapter, therefore we can write the above equation minus dn by dt it is equal to the n1 minus n2 into the V12 into the row of mu. Now say as this is equation number 1. If the energy density of the light field in the medium is rho nu, then the intensity I is given as the I it is equal to V, the rho of nu into the V. Now here the V is the velocity of the light in the medium and the V it is equal to the C divided by the mu. But the intensity of the but the density of the medium is expressed in terms of the NH nu. Therefore, we can write the expression of the intensity I it is equal to the NH nu into the V. Therefore, we can write here the N it is equal to V, the I divided by the H nu into the V. The loss of the photons minus dn is a small thickness dx of the medium. Therefore, we can write the loss of the photon in a small thickness dx of the medium by taking the differentiation of the above equation. Therefore, we can write the minus dn it is equal to the di divided by the h nu into the v. By multiplying and dividing dx on the RHS of this equation, so we can write minus dn it is equal to the di divided by the h nu into the v into the dx divided by dx. The net rate of the loss during a time interval dt can be obtained by dividing dt to the denominator on both sides of the above equation. So we can write minus dn by dt it is equal to the di divided by the h nu into the v into dx divided by the dx into 1 divided by the dt. So by the rearranging the terms here, we can write the minus dn by dt it is equal to the di divided by the dx into 1 upon h nu into the v into dx divided by dt. Now say as this is equation number 4. But we have already studied about the intensity of the incident radiation when it is passing through the medium of the thickness dx. Therefore, we can write the equation of the intensity, that is the change in the intensity. The di it is equal to be the minus alpha into I into the dx. Now here the alpha is the absorption coefficient. Now by rearranging the terms, we can write minus di by dx it is equal to the alpha into the I here. We know the velocity. We can write the v it is equal to the dx divided by the dt. Therefore, the equation number 4 becomes, by substituting the values of di by dx and v So the equation number 4 becomes dn by dt it is equal to with alpha into I into 1 upon h nu into the v into v, that is the velocity. Therefore again here by substituting the value of I, we can write this equation as dn by dt it is equal to with alpha into rho nu into the nu multiply by 1 divided by the h nu. By cancelling the terms here the v. Now then by comparing the equation number 1 and 5, okay, now this is the equation number 1 here. So by comparing these two equations, now we can write here the rho, we can write here the alpha into the rho nu into the v multiply by 1 divided by the h nu, it is equal to the n1 minus n2 into b12 into the rho of nu. Therefore we can write here alpha into the v into 1 upon h nu is equal to n1 minus n2 into b12. We can express it in terms of the alpha, that is absorption coefficient. It is equal to the n1 minus n2 into h nu divided by the v into b12. Now here this equation number 5 relates the absorption coefficient alpha to the difference in the population, that is n1 minus n2 of the two energy levels. For a material in a thermal equilibrium, now we have already studied about the condition of the thermal equilibrium. Then for a material in a thermal equilibrium, N1 is greater than the N2 and alpha is the positive here. Therefore, that is alpha is positive if the N1 is greater than the N2. But if N2 is somehow made greater than N1, then alpha becomes negative quantity and the relation of the intensity becomes here. Now that means here when the radiations which are passing through any material, then the intensity of that radiations can be expressed by using the equation I is equal to with I0 into the e raised to minus alpha x. Here alpha is the absorption coefficient. Now if we write this equation in terms of the I is equal to with I0 into the gamma x, where gamma is equal to with the minus alpha and which is referred to as the gain coefficient per unit length. That means instead of that minus alpha, if we write the gamma, now then here this gamma indicates the gain coefficient. Now as the gain coefficient is positive quantity, then the equation 6 implies that the intensity of the light grows exponentially as the light beam travels through the medium. That means from these equations we can say that the exponential term is positive. So the I it is equal to the I0 into the e raised to gamma x indicates that the intensity of the radiations when passing through any material goes on increasing here. And this is clearly shows that there is the amplification of the light here. Therefore, the equation number 5b, we can write the equation number 5 as the alpha it is equal to the minus in bracket n2 minus n1 into h nu divided by the v into the b1. So we can write minus alpha, it is equal to the n2 minus n1 into h nu divided by the b into b of 1 2. Now by substituting the value of minus alpha, those we have taken equal to the gamma. Therefore we can write the equation gamma, it is equal to the n2 minus n1 into h nu divided by the b into b12 here. And this is the condition of the light amplifications. Now that means here, by using the artificial, by using the external agency or by using the any external method, we can made the N2 or the population of the higher energy level is greater than the lower energy level. Then the equation becomes gamma, it is equal to the N2 minus N1 into h nu divided by the v into the b of 1 2, and this is the condition of the light amplification. So here the gamma will be the positive if n2 minus n1 is greater than the 0, that is n2 is greater than the n1, that is the population of the higher energy level is greater than the population of the lower energy level. And we know that this is the condition of the population inversion, those we have already studied. So with the help of the any external method or the any external agency, we can achieve the population inversion, and that method is known as the pumping method. Now we will see in the next lecture. Now by using the relations for the Einstein coefficients B12 and A12, and the one of the relation, that is C is equal to the mu into the V. The relations are here the A12 divided by the B12, it is equal to the 8 pi h nu cube into the mu cube divided by the C cube. Now where the A21 is the Einstein coefficient of the spontaneous emission and B12 is the Einstein coefficient of the induced absorption. One of the relation of the Einstein coefficients of the spontaneous emissions, we can express it in terms of the reciprocal of the lifetime, that is tau. Now here the tau is the lifetime of the spontaneous emission. Now by taking the reciprocal of this ratio, we can write the B12 divided by the A21, it is equal to the C cube divided by the 8 pi h mu cube divided by the mu cube. We can express it in terms of the B12. Therefore the B12 it is equal to B, and by substituting the value of the C here, the B12 it is equal to be the mu into the V bracket cube into the A21 divided by the 8 pi h nu cube into the mu cube. By substituting the value of A21, we can write here the mu cube into the V cube divided by the 8 pi h V cube into the mu cube into 1 upon the tau. So we get the B12 it is equal to the V cube divided by the 8 pi h mu cube into the 1 upon the tau here. Therefore the equation number 6 we can write here by substituting the value of the B21, that is gamma, it is equal to the n2 minus n1 into the h nu divided by the v into the v cube divided by the 8 pi h mu cube into the 1 upon tau here. Therefore the gain coefficients we can write finally the gamma, it is equal to the n2 minus n1 into the v square divided by the 8 pi mu square into the 1 upon t. So remember here students how to obtain the gain coefficients. that is the how to obtain the relation of the gain coefficient, that is gamma, it is equal to n2 minus n1 into the v square divided by the 8 pi v mu square into the 1 upon t. That means here the gain coefficients in terms of the population inversion or the difference between the population of the two energy levels and the lifetime. Students, now in these lectures we have seen about what do you mean by the active medium and the condition for the light amplification. So the students, you have to be remember here what is meant by the active medium and what is the condition for the light amplification and how to obtain the expression for